In this example, we're asked to look at the free response of a single degree of freedom system that's hanging under its own weight. We know the mass of the block, we know the static deformation, but what's different about this is that the spring is not a linear spring. The restoring force is not proportional to the amount of stretch or compression. Rather, it is a cubic function of that stretch or compression. What we want to do is, for the known equilibrium state, calculate what the natural frequency for small oscillations will be about that equilibrium state. We need to know our equation of motion. In order to get equation of motion, we need to draw an F in FBD. The forces we have acting are going to be the spring force Fs. There will be the weight force of mg. And the problem says that we're going to let x be measured positively downward. Whenever we we sum the forces in x, we have Fs pointing in the negative x, the weight in the positive x, and that's equal to ma, so that's mx double dot. So we have equation of motion mx double dot plus Fs, which is kx, plus beta x cubed minus mg is equal to 0. And for later usage, we might refer back to that as being f of x. But f of x is, keep in mind, is just Fs minus mg. We know something about static equilibrium. Static equilibrium corresponds to when x double dot is a 0. So it says that static equilibrium occurs when k xeq plus beta xeq cubed is balanced out by the weight. So basically it says that the spring force is equal to the weight. From this, we can calculate what the numerical value for beta, mg minus k xeq divided by xeq cubed. We know the mass m. We know the stiffness of the spring was 500. It's given to us that the static equilibrium is 0.01 meters divided by 0.01 meters cubed. And so calculating the value of beta, that's 4.8 times 10 to the 6th Newton per meter cubed. So what we have at static equilibrium, let's make a sketch here of Fs versus x. We know that that's a cubic function like this. What we also know is that when the weight is balanced out by the spring force, so when Fs is equal to mg, that's the equilibrium state. Our goal here is to determine the slope of this line, because that's going to be the effective stiffness that we have of that spring at that equilibrium state. To get to that point, what we will do is we'll write the spring force Fs in terms of a Taylor series expansion. So this would be Fs at the equilibrium value, dFs dx at equilibrium, x minus equilibrium, and then, of course, there are higher order terms. This is just a representation of the Taylor series for the spring force there of Fs. We know that at equilibrium, Fs is equal to mg. dF ds, that's going to be equal to k plus 3 beta xeq squared times x minus xeq like this, dot, dot, dot. And based on what we've done before, we're going to say that the variation of x from away from the equilibrium state is going to be what we're going to be calling z. So I substitute this back into the equation of motion. And truncate that Taylor series expansion after the linear terms. What I get is mz double dot plus mg plus k plus 3 beta xeq squared times z is equal to mg. The weight terms cancel out. If I divide through by m, I get z double dot plus k plus 3 beta xeq squared divided by m. Z is 0. So this is the linearized equation of motion. The linearization was done about the equilibrium state. This is, for small oscillations, what the square is of our natural frequency. So natural frequencies for small oscillations about that state, it's the square root of k, which we know, 3 beta, which we know, the equilibrium state we know, squared, divided by m, like this. So this is the frequency of small oscillations about equilibrium. And that's what we want. Some comments here are worthwhile, I think. The comments are that for linear systems, we have seen that natural frequencies are not dependent on gravitational forces. It's just the effective stiffness K divided by m with a square root. Gravity does not come into play. Said in a different way, an oscillator moving on the Earth would have the same natural frequency here as it would on the moon, where the gravitational attraction is far less. So it doesn't depend on G. For nonlinear systems, particularly those with nonlinear stiffness, we see here that natural frequencies can depend on gravity. Because gravity influences the static deformation, and therefore it influences the state about which the linearization is done. So this begs a question. And here's the question. We know that for linear systems, we know that omega n is the square root of k over m. For this system here, it's over m for sure, but there's an equilibrium value here. This says that if you increase m for a linear system, the frequencies go down. This equation, it's not clear. So I'll leave this as a question for you, is for this system. Does an increase in mass m lead to an increase or a decrease in natural frequency omega n? And it's not clear, because as we look back at the equation, as you increase m, obviously you have a 1 over m effect. But as you increase m, you also increase the equilibrium deflection, effectively increasing the stiffness. So an increase in mass actually increases the slope of this curve that I drew here. As you move up, the slope increases. Which one wins out? Is it the 1 over m, which would bring it down, or is it the increase in equilibrium state, which would make it go up? Think about that, and maybe give me an answer.